So in this section, we deal with things called projectile motion. Now, a projectile is an object that is being accelerated due to gravity, but which also has a horizontal component to its motion. We need to take both of these into account, and we need to take them both into account separately. So we need to make a mental note of separating what is vertical versus what is horizontal. Then at the end, if we need to recombine them, we'll do that, but only at the end. So we have a ball that is thrown off a balcony and has an initial velocity of 18 meters per second horizontally. So the ball would essentially be making this kind of motion as it flies. I want to determine the position of the ball at 1 second. So obviously, because this ball is falling, it will be below where it was thrown. It would also be to the horizontal. Dealing with projectile motions, dealing with the horizontal piece first is the easiest. What we know is that the speed horizontally is 18 meters per second. And that is a constant speed. Anytime we're dealing with projectiles, the horizontal speed will be constant. We know the amount of time that's gone by, 1 second. And what matters is the position or the displacement. Since we have a constant velocity, we can use one of the simpler equations. This one would work just fine. Substituting in, and cross multiplying, we would get that the displacement horizontally would be 18 meters. The vertical motion we need to think a little bit more about. We know the acceleration vertically will be 9.8 meters per second squared down because we have gravity affecting this motion this way. We know the amount of time that's gone by, 1.0 seconds. Now, we cannot use the 18 meters per second because that is a horizontal velocity. Has nothing to do with the vertical. We do, however, know the VI of this vertical motion. And if this ball is thrown straight horizontally, its initial downward motion is 0. And what we're trying to solve for is the displacement vertically. So again, keeping the vertical and horizontal separate from each other is key. Looking at these variables and looking at the list of equations, there's one equation that pops out that is the best. Delta D equals VI delta T plus 1/2 A delta T squared. Substituting in, and I apologize for the squishiness of that, but I was just out of space. Calculating this out, 0 times 1 gets 0. 1/2 times 9.8 times 1 squared is 4.9. So the displacement in the downward direction is 4.9 meters down. So this ball has flown 18 meters horizontally and 4.9 meters down. Knowing that, we can determine the final position. So what this ball has really done is it has gone 18 meters horizontally, 4.9 meters down, and what we're actually concerned with is this position here. Because it's a right triangle, we can use Pythagorean theorem. Going to call A 18, B can be 4.9. (18 squared is 324. 4.9 squared, 24.01. Adding those together gives 348.01. Taking the square root, going to 2 sig figs, we get 19 meters. And as with any motion in 2 dimensions, we do need to know the specific angle that this is moving at, which would be this angle here. It's a right triangle, so SOHCAHTOA is good to use. We have the opposite, 4.9 meters. We have the adjacent, 18. So we use tangent. Filling in 4.9 and 18. Calculating that out, make sure your calculator is in degree mode. 2 sig figs again, we get 15 degrees. So putting this all together, the overall position of this ball would be 19 meters. And the way that we put this direction is not dealing with north, south, east, west, because we're dealing with vertical and horizontal. The easiest way to put it would be that the ball is 15 degrees below the horizontal.